Man, I wish we lived in the 21st century. My eyes hurt.
Me too. I'm so hot. That's better.
You can say that again.
That's better.
We're gonna find out how old these things work.
Get ready.
It's science time. How does it work?
Can I eat it?
What's that smell?
Will it explode?
Ooh, can I touch it?
Science is like that. The more you learn, the more questions you have.
It's science time.
Scholastic Scrimmage is sponsored by St. Luke's University Health Network, the region's leading provider of medical education. For more than 100 years, St. Luke's has been dedicated to educating physicians, nurses, and healthcare professionals. To learn more, call St. Luke's InfoLink, toll free at 866 St. Luke's, or visit sluhn.org.
Introducing new Lutron dimmers with technology that reliably works with dimmable CFL and LED bulbs. Remember, the more you dim, the more energy you save. To learn more, go to LutronSavesEnergy.com. Available from electrical contractors, lighting showrooms, and home centers.
Uh-oh. I took apart Dr. D's flashlight and I can't figure out how to put it back together.
Why did you do that?
I was curious to see how electricity works. Here's a switch for the flashlight. Why does a switch turn a light on and off?
Well, here's a switch for the lights.
Hey, who turned out the lights?
Oops.
And what happened to my flashlight?
I'm sorry, Dr. D. I just want to learn more about how electricity works. Like this flashlight, for example. How does a switch work? And with the batteries, why do you need to connect something to both ends instead of just one?
And why does electrical plugs, they always have 2 or 3 prongs?
Well, because there are 2 slots in the outlet.
Oh yeah, very helpful.
Well, these are very interesting questions. They lie at the very heart of electricity in a field known as electronics. Hey, do you guys want to learn more?
Yes.
Yeah.
Let's go on a field trip.
Hey guys, it's Brittany here. We're at the Da Vinci Science Center in Allentown to learn about some electrifying stuff. Come on. Okay, Tyler, so what do we have here?
This machine is called Jacob's Ladder, and Jacob's Ladder is a device that produces electricity through an electrical spark gap. And as we hit the button here, you see that the electricity starts at the bottom, and then it will eventually, once it heats up, move its way to the top.
And it changes color.
So as it's rising, it changes the color because it's cooling at the same time. So at the bottom it's blue, here you see it white and a little bit of yellow.
Very cool. So Tyler, I know what this is. This is an electric meter, and they're found in every home.
Yes.
What is this exhibit showing us?
Well, this exhibit is showing us how to read an electrical meter. You see there's these small little dials here numbering from 1 through 9. That's what the professional would read, but personally, you'd read this little disc here that will move, showing you how much electricity you're using throughout the house.
So the faster it's spinning, the more electricity you're using?
Correct.
Which one do you think uses the most electricity?
I think the drill uses the most. The hairdryer. Look at how fast that's spinning. So the hairdryer uses the most electricity. What about the light bulbs?
The incandescent light bulb actually does use a lot of electricity.
Oh, that's interesting. So the fluorescent light bulb uses the least amount of energy, and the hairdryer uses the most.
Now that's some shocking stuff.
For Science Time, I'm Brittany Garzillo.
Electricity, the flow of electrons in a wire.
Volts, a measure of the force that moves electrons through a wire.
Electrician, a person who specializes in electrical wiring, like the wiring in your house.
Complete circuit, an arrangement of wires, a circuit, in which electric currents start at one end of a source, such as a battery, and ends at the other end.
Circuit breaker, an automatic switch that cuts off electricity under certain conditions, such as those that might cause a fire.
Want to hear a joke? What's an electrician's favorite flavor of ice cream? Chocolate. Okay, why did the ceiling lights go out? They got tired of hanging around the house all day.
Any more jokes like that, and I'll have to charge you with assault and battery.
Let's go to the laboratory.
What's this?
Oh, that's an old digital display converter circuit diagram.
That looks complicated. I didn't think I could ever understand that.
Actually, you could. You're pretty smart. But not right now, because you haven't had any experience with simpler circuit diagrams. Would you like to see one?
Yeah.
This is a simple circuit diagram.
It still looks pretty complicated. It's almost like hieroglyphics.
It's all Greek to me. Well, Egyptian anyway.
Well, I don't think it's as bad as you think. How about we build one of these using real parts? Would you like to do that?
Yeah.
Yeah.
Well, battery, switch, light bulb. See if you can figure out how to do that.
Yes. Let's set them up like this. So we can put the switch up top, the battery over here, and the light bulb over here.
Good idea. So it looks like the picture.
Yeah. So we're gonna need wires in between, but we gotta figure out which ones to use. This end won't connect to this end. I think this is the one we're looking for, because this one sticks underneath the screw and it connects to there.
Okay.
Do you know what you call that?
No idea.
A lug, but we're just going to call it a fork.
Right, so you put these two together, and so you put one of these on top, I guess.
Yep. Lefty-loosey, righty-tighty.
And what do you call those things again?
Wire nuts?
Wire nuts, yes. Kind of goes on like a hat, doesn't it?
Yeah. So you put this.
It's not gonna fit unless we loosen it, though.
Okay.
So let's loosen this up. Okay. And will it fit?
Let's see. Yeah.
Okay, let's tighten it. Got it?
You're really good with that screwdriver.
Thanks. Okay. And then
Is that this right here?
light bulb.
Light bulb?
So you do one end and I'll do the other.
Yeah.
You're doing great.
Okay.
All right.
So they're all together now. 3,
2,
1.
Yeah.
It worked.
It lit up.
That wasn't nearly as hard as you thought it was going to be.
No.
Was it?
No.
Do you
It's pretty
realize
easy.
that your house is wired using many of these same parts? Do you realize there are probably hundreds of wire nuts like this in your house and probably thousands in this laboratory? Wow. Now let's see if you can answer any of the questions that you raised earlier. For example, why does the switch turn the light on and off?
The wire must disconnect itself so the electricity can't get to the bulb.
Like in the diagram right here.
You can see that the switch is in a position where the electricity couldn't go through. This would be like the switch being off. And if this were down touching there, the electricity would be able to go all the way around and the light bulb would be on.
Yeah, so it has to go all the way around for it to work.
And we call that a complete circuit.
Yeah.
And that's why it needs 2 prongs.
It needs to start
Complete
there
circuit.
and end there. So there are 2 points of contact, which is in fact exactly the answer to your question, why do the plugs have 2 prongs? Let's see how they use these concepts in the real world.
Every day, we're using hundreds of different products. But have you ever stopped and thought about how these products are made or where they're made? Thanks to science, all of these things are possible, even all the products we make right here at Lutron. I'm Melissa Andresco, and I'm the Public Relations Director at Lutron Electronics. And we make everything from a dimmer to use on your bedside lamp, to motorized window shades, to systems that control entire football stadiums, shopping centers, and office buildings.
For some of our dimmers, we can pack up to several hundred electronic components inside this very small space. There's a lot of science packed into these little dimmers. Hi, my name is Tim Majewski. I'm an engineer here at Lutron Electronics. We use an electronic switch inside that can turn the lights on and off 120 times every second. And by varying how much we turn the lights on and off with that switch, we can change the brightness of the light bulb. I'm sure you're familiar with this device. This is an iPad. I'm sure you play games on it, watch movies, surf the internet, right? And Lutron has created a new innovation where you can actually control your lights and your motorized window shades from an iPad.
Dimmers also save energy. In the US alone, dimmers save about 10 billion kilowatt hours every year in energy. And what does that mean? About $1 billion in utility costs.
What about stuff like computers and smartphones? You know, digital devices. These kinds of devices actually make decisions. Sometimes these decisions are so complicated that they almost seem like magic. But believe it or not, each of these complicated decisions is simply the result of a huge number of very simple decisions. Some of these simple and basic decision makers can be demonstrated using a series and a parallel circuit. Why don't we visit a local school? What we're going to do now is we're going to give you a chance to build electrical circuits to route that energy through a switch and through a light bulb. How would you like that?
Yes.
Okay. Oh my goodness, that's beautiful. Can you tell me why the switch is there?
So you could open and close the circuit to turn off and on the light.
Did you have trouble making this circuit?
No.
Were you afraid?
No.
Did you follow the diagram?
Yes.
That's what we want to see. Everybody is wiring a series circuit except for one group. Why don't we go over and take a look at what they're doing? This group here, they're doing the harder parallel circuit. You guys doing okay?
Yeah.
Okay, good work. You designed circuits that make decisions. This is the basis of every electrical device of any complexity that you have. Because you see, even though that looks like a simple decision, when you put millions or billions of those together, you can perform something that appears to be magic. And yet it's real.
What's this?
This is a voltmeter. This is used by electricians and scientists and engineers to measure the voltage across 2 points in a circuit.
Can I touch it?
Yes, you may. Would you like to find the voltage across the light bulb when it's turned on?
Mm-hmm.
Well, turn the switch on and let's touch the two ends to the two ends of the light bulb
Like
and
this?
see what it says. Yes, push real hard.
1.46.
So about 1.5.
About 1.5, and that's exactly what you'd expect for a flashlight battery because it's 1.5 volts.
Oh, cool. How do light bulbs work?
Well, this is an ordinary incandescent light bulb. In fact, we can turn this on and even make it go brighter or dimmer. Now, do you see that little piece of metal that looks like a spring across there? That's a filament of a metal called tungsten. That gets very, very hot as the electricity goes through it, and it gets so hot that it glows. But one of the problems with these kind of light bulbs is that they give off a lot of their energy in the form of heat, which is kind of wasteful. So more modern light bulbs are the compact fluorescents and the LED light bulbs that you see in stores now.
And they don't give off heat.
And they don't give off anywhere near as much heat, so they're very, very energy efficient. Yeah.
How do electric motors work?
Ah, now that's more complicated. How about we build the world's simplest electric motor? You want to try it? Okay. We take a coil of what's called magnet wire, and we're going to wrap it around a battery because it's just about the right size. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Here, watch this. I'm going to cut it off. I'm going to pull it out like this. I am going to wrap this around here on one end, and I'm going to wrap it around on the other end. And then what we need to do is we need to cut the ends like this and like this. And you see, this is insulation on here, believe it or not. What you can do, what you can do is you use a scissors, you put it on flat on a table, and you scrape it off only one side of each of these two prongs. And you end up with a coil of wire that looks like this, where the metal is exposed on one side, but not on the other. The next thing we do is we take an ordinary large-sized paper clip. We straighten it out so it looks like this. We use a pencil to put a little loop on one of the ends. We do that for 2 of them. And now what we do, and here comes the fun part, we take a battery, we put a rubber band around it. These are going to hold our paper. This is going to hold our paper clips. I put 1 paper clip on one side, 1 paper clip on the other side.
To make it symmetrical.
To make it symmetrical. There's that word again. Keeps coming up over and over again. And I take some magnets, like ceramic magnets, and I stick them right on the battery.
Okay.
Now, can you hold that for me?
Yep.
Because I'm now going to take the finished coil of wire, and we're going to put it right here.
Awesome.
That's so cool.
How is
The
that
world's
happening?
simplest electric motor. You see, what's happening is that when the electricity makes contact with the copper, it turns this into an electromagnet that gets pushed by this regular permanent magnet. It gives it a kick, and that's how it keeps on spinning.
cool.
That's how the motors, for example, in air handling systems work, or even perhaps one of your cat's favorite toys.
Hey, I found my old rock collection. Some of these are from my trip out west.
That's quite a collection. Do you know what they're called?
Well, this one's pyrite and this one's granite.
Did you buy this at a store? There's still a sticker on it.
I don't think that really matters. I mean, you could know the names of many rocks and actually know nothing about them at all. What's in a name? That which we call a rose by any other name would smell as sweet.
Huh?
Shakespeare. But never mind that. The point is that names of rocks do become important for scientists, but we're more interested in the story that a rock has to tell.
Huh?
Well, rocks don't actually talk, but they do tell a story of how the Earth was formed, a story going way back in history.
Do you know what this rock is saying?
Oh, goodness, no. I'm not a geologist. A geologist is a scientist who studies rocks. But it doesn't mean that I can't be very interested in them, and it doesn't mean that I can't learn a whole lot about them. I love photography, and I know a lot about it, even though it's not my job. And I'm even pretty good at it. But it's not my occupation. It's not my job. It's a hobby. And just like science, you don't have to be a scientist to enjoy science and to even learn a lot about it. Do either of you know the difference between a rock and a mineral?
Well, a rock is a compilation of different minerals.
That's right. Now here on the table, I have 4 specimens. 1 of them is a rock, and 3 of them are minerals, and that rock is made from the other 3 minerals. Can you figure out which one of those 4 is the rock?
How did these get here?
For 10 points in the game, which one is the rock?
Ooh. Ooh.
Dang it!
This is the rock. It's made up of all these 3 minerals.
That is correct. Excellent work.
I knew that. This one's granite, this one's biotite, this one's quartz, and this one's feldspar, and all 3 of these are in this one.
That is correct. But do you know the 3 different types of rocks?
Igneous, sedimentary, and metamorphic. I remember their names, but I don't remember what they mean.
Well, let me give you a hint. Igneous is the Latin word for fire.
Oh, so rocks that come from like cooled lava and magma.
That's exactly right. The next type of rock is...
Those are sedimentary rocks, and they're formed when you have little tiny particles and they all settle together and stick. And then they form in layers.
That's exactly right. And I can give you a hint about metamorphic. The word metamorphosize means to change form.
Oh, that means that from heat and pressure in the earth, the rock changes from one state to another.
That's exactly right. Now, what I'm going to show you now are 2 igneous rocks. Now, I want you to take a look at these rocks and, like a scientist, characterize them. Tell me something about them.
Well, they're very different.
Okay, they are very different.
This one has big crystals.
And this one has really, really little crystals, and it feels like sandpaper.
Yeah.
Would you believe that these two come from exactly the same melted rock?
Really?
They do. And that's how a rock tells the story about how it was born. You see, granite is magma that cools and hardens deep underground, where it has a blanket of dirt on top of it. Now, if you have a blanket on you, doesn't that keep you warm?
Yeah.
Well, same with the granite. As it's cooling, it's kept warm, so it cools off only very slowly. It cools so slowly, it has time to grow big crystals. But if that very same lava comes to the surface and cools quickly, it cools so fast it doesn't have time to grow big crystals. And
So it has little ones.
Little tiny crystals, exactly. And you said it felt like sandpaper, and that's a good description. If it cools deep underground, it becomes granite. And if it cools on the surface quickly, it becomes rhyolite.
Magma, molten rock located underground.
Lava, molten rock located on the surface.
Mineral, a natural crystalline solid with atoms arranged in a certain way.
Rock, a solid mixture of one or more minerals.
Igneous rocks, rocks that form when mixed up melted minerals cool and harden.
Sedimentary rocks, rocks that form when loose particles of rocks or shells are stuck together.
Metamorphic rocks, rocks that have been changed by heat or squeezing.
Hey Josh, my geology teacher is really upset.
Why?
All the students take him for granite.
That's just terrible, James.
My sediments exactly.
If you want to see really, really big rocks, I mean really big ones, check out Columcille Park in Bangor, Pennsylvania. The rocks here are so big, they're called megaliths. That means giant standing stones. There are almost 100 of them here.
Last year we had over 7,000 visitors from around the world.
Bill Coy, the park's creator, handpicked each of these giant standing stones. They used trucks and cranes to move them and set them into place. Some of the rocks are granite, like these stones near the pond, but most of them came from just 3 miles away.
3 miles down the road, they dug shale for road beds. That's a crumbly stone. These boulders were locked in the lining of that shale, which was mud under the Devonian Sea 400 million years ago.
That's right. Some of these rocks are 400 million years old. This one stands more than 20 feet tall and weighs 45 tons. This structure is called a dolmen, and it's made of 3 stones. 2 stand upright, and 1 lies across them, like a table. And look, this one even has some fossilized organisms inside of it. Hey, can you think of a famous collection of megaliths? How about Stonehenge in England? It's also a collection of megaliths like these.
Let's go on a field trip.
Hey guys, Brittany here. I'm getting ready to rock at the Da Vinci Science Center in Allentown. Come on! What can we learn from these fossils behind us?
Well, there are a bunch of things we can learn, Brittany. So one of the things is that we can look at fossils in old rocks and fossils in young rocks, and we can look at some of the differences that happen. So over here, for example, we have a shell, and it looks not that different from a shell that you would find today on the beach.
It doesn't. It
But
looks
this
like
one is about 200 million years old. This shell is about 20 million years old, and you can see that there's some differences between them. And so that's one of the things that geologists and paleontologists would study. They would look at the differences to understand how animals have changed over time, how they evolve.
So they can look at evolution based on looking at a rock or a fossil.
Exactly, because this is a record of a living thing.
You can find fossils anywhere in the world. This rock is from Pennsylvania and is more than 250 million years old.
What you can see in this rock are a lot of fossils, but they're not fossils of animals, they're fossils of plants. And so we have ferns, and we have some branches, and we have another branch over here with some skin on the outside of it. These are things that don't live in Pennsylvania because it's too cold here. So these are plants from a tropical climate. So not only can we say something about what used to live here, but we can also say something about what the climate used to be like. It used to be warm and wet and swampy.
Right here in Pennsylvania?
Absolutely.
You can take part of the fossil record home by creating a rubbing.
We can just take a piece of paper and we can take a pencil and we can lay it over one of our fossils and just rub back and forth with the pencil, and the design of the fossil will come through on the paper.
That's all for me today. For Science Time, I'm Brittany Garzillo.
Why don't we visit a local school? We're going to learn all sorts of things about rocks, and we're going to look at them real closely. Let's look at these 4 rocks: galena, calcite, olivine, and pyrite. As you look, think about their properties and the words you can use to describe them. Galena has a silver gray color and feels very heavy because it has lead in it. Calcite is smooth, shiny, and often see-through. Olivine is bumpy and appears green. People make jewelry out of it. Pyrite looks so much like gold that people used to think it was actually gold. Hey look, it's my friend, the science reporter, Rocky Rock and Roll. Let's tell him about these rocks. I'm here at the Asa Packer Institute of Science and Rockology, where scientists are hard at work studying rocks. We're gonna come over here to this workstation first, and you! What is your name, please? Dr. Anthony. Could you please describe that interesting looking rock there? Bumpy, and what color is it?
Green.
Green, yes, very, very interesting discovery. And you! What is your name, please? Rachel. Dr. Rachel. Could you please tell me something about that interesting looking rock? What color does it look like? What does it look like? Gold! It looks like gold. Some people used to be fooled into thinking that was gold. That's why they call it fool's gold. Person used to say, gold, I'm rich, I'm rich. And everyone would say, that's not gold, you fool. Bye-bye, everybody.
You can try this at home. Here's what you need: a piece of chalk and a glass of vinegar. You ready to do it? Yes. Okay, all you need to do is drop the chalk in the vinegar. Okay. Simple. Wait for it, and there it goes. Oh my gosh. The calcite in the chalk is dissolving. How does it work? Well, minerals that contain calcite dissolve in acids, like vinegar.
See you next time on Science Time.
Introducing new Lutron dimmers with technology that reliably works with dimmable CFL and LED bulbs. Remember, the more you dim, the more energy you save. To learn more, go to LutronSavesEnergy.com. Available from electrical contractors, lighting showrooms, and home centers.